Hello. So I talk about this notebook, which is available to Wolfram webpage. So this is about Kepler problem. So in Kepler problem, you have, for example, a planet going around a sun, and we are used to elliptic circular orbits. However, for example, for Mercury, this orbit no longer closes. Yeah, so it precesses. So this is about trying to understand it numerically. So if we add this rotation of one object in gravity or electromagnetically a magnetic dipole. So many particles have magnetic dipole, so should be crucial, especially for scattering of the particles. And so here is a nice animation that we can see that the initial angular momentum grows. Yes, so here is near zero, and now it grows, and now we go to the ellipse, circle, Kepler, and we escape. But for very small, you can see that this interaction of this rotation or magnetic dipole makes the scattering much more complicated. So we will discuss it. So here is a simulator you should be able to play with if enabling. So here you can enable calculations. Okay, so the question is, do we focus on gravity or electromagnetism? So turns out they are very similar, especially in practical approximation called gravity electromagnetism. Yes, so standard Coulomb interaction, just attraction and repulsion, is not Lorentz invariant. So it's crucial that we add magnetism to make it Lorentz invariant. The same we can do with gravity, with Newton force. We should add this gravity-magnetic field, so-called, to make it Lorentz invariant. And this is now the first correction to Newton approximation of general relativity. That was directly tested by the gravity probe beam, the most famous test of gravity above Newton. Yes, so we need this second set of Maxwell equations. So now we can imagine that we have a dipole, but it could be also dipole coming from this rotation of a star or a planet. Yeah, so we think about Kepler problem, that there is one central heavy object and there is rotating around light object around, and one of them is rotating or is a dipole. Yes. So here is a basic problem in electromagnetic view. So it is simpler to use, and we can imagine this is, let's say, a Bohr model. It's classical, but still it's very popular, for example, for Rydberg atoms. There are very large atoms for which they use Bohr model. So first we need to find the Lagrangian. And so here is the Lagrangian. Here we can see the kinetic energy, and here is the potential energy because of the central charge of the nucleus. So there is this Euler-Lagrange equations which can allow us to find the evolution, and if we use them, here is a mathematical source that we add this Lagrangian, use these Euler-Lagrange equations, and it finds the evolution, the second derivatives with the force coming from Newton or Coulomb force. So there is also invariance allowing for conservation law to the Nether's theorem. So time invariance allows us, says that energy is conserved. And we have also rotational invariance. You get the central object and you can rotate and it doesn't change the equations, leading to angular momentum conservation. Okay, so here we solve this simple differential equation, getting well-known circular ellipse Kepler solution. Okay, so now let's think about adding this magnetic dipole. So mathematically, this is a dipole, and for dipole, here is the formula for the A field, and it's Carroll magnetic field. So here they are shown as vector fields. Yeah, so the A and B fields. And to include them in Lagrangian, there is used this A dot velocity and times charge. Yeah, so this is this additional term in Lagrangian we need to include to add this magnetic dipole moment of one of the object, or in gravity if one of them is rotating. So now the final Lagrangian looks like this. Yeah, so here you have the Kepler part, the kinetic term, the potential term, and now this interaction of this magnetic dipole with some charge or gravity or mass in gravity. So here we can find the Lorentz force and acceleration and this acceleration in the spherical coordinates. So we can simplify the formulas. There are sometimes there are problems with latex here, but you can, if you do enable there is no problem, but there are different problems. So, okay, so here is this basic form where you can find these parameters. But the most crucial, so we can in this case C to 1, but the most crucial is the CS, which says how strong is this magnetic dipole. Usually it's tiny, it's many orders of magnitude below 1. And moreover, we can see that it's 1 over distance square. So it's tiny, but for very small distance, it becomes important. So if you have this Kepler, this circular high angular momentum orbits, then it's negligible. But if we just have low angular momentum, free fall, then especially very close to this object, it becomes very, very important part. So we see that indeed so it is literally Lorentz force. This force, it's literally Lorentz force coming from this magnetic field, and it will literally auto to forbid this particle to collide. So it prevent, for example, electrons to collide with the nucleus. Okay, so here is the nether theorem. Still, the energy is conserved given by this formula. However, there is problem with this rotational symmetry because we have the spin now. We have one directional spin. So now there is no longer symmetry for this rotation, but there is still rotation, symmetry for the rotation around the spin. So there is only one angular momentum survives, and it's given by this formula. So this is conserved. And we can find these formulas in spherical coordinates. So here is the energy, standard 1, also for Kepler, and now one angular momentum with this addition of this dipole interaction. So we can also find the formulas using these two conservation laws. So now let's go to numerical simulations, going straight from this standard Lagrangian, this Kepler plus this interaction of magnetic dipole with charge. So Mathematica finds other Lagrange equations here. Symbolically, we get these formulas, a bit more complicated than standard ones. And now let's take a look what's happening for 0. If we start in plane perpendicular to the spin. So I now assume that the spin is in zero direction. So the spin is 0, 1, 1. So here is the spin is 0, 1, 0, 0, 1. So in the z direction. So now we will focus on behavior in z equals 0. So this axis, xy axis. So here we start from 1, 0, 0. Yes, from x. So we start here. And it falls, the particle falls, and now there is this Lorentz interaction. It becomes crucial, and we can see that it prevents the collapse onto the central object. So our let's say electron could not fall into the proton because of the Lorentz force. Instead, it was scattered 120 degrees. And turns out it's exactly 120 degrees. Very, very nice result I will show in a moment. So after three such quantized kind of steps of nearly constant time, we get back to the original position. So we get closed orbit of this type, made of three scatterings. Okay, so for this proton scattering of this time, so this is time of just falling to the 0. So we can see that this is twice, this is 4 times, 6 times. So we have multiplicities of this basic time of this falling to nearly 0. Okay, so here is the calculation that we get exactly 120 degrees. So we have these two conservation laws. So one is energy, and one is angular momentum. This perpendicular to our spin. And here it is assumed that they are 0. So angular momentum 0 means free falling. Energy equals 0 means falling from infinity. So this is this asymptotic falling. In practice, it's non-zero, but for 0, we can calculate this is exactly 120 degrees. So let's assume this is indeed 0. So here we have this derivative of change of phase. And now we get the reduced the time derivative. And what we can see that it can be zero. So now for the minimal radius, we need to find where this is zero. So we can find this minimal distance and this formula. So so now we need to integrate this change of angle with radius from this minimal distance. And if we do it, we get this 120 degrees. So it is very nice that it's universal, that whichever parameters, magnetic dipole moment we choose, it should be exactly this one. Yes. However, this minimal distance depends on the parameters, like the strength of magnetic dipole and so on. So for example, to get some intuitions, if you take electron proton, this minimal distance is like 47 femtometers. So it is for proton is like 1 femtometer, so this is like 50 times larger than proton. So it is small, but large in comparison to proton. However, it can be reduced for different angular momentums a bit, like 2.5 times the bottom. And for larger nuclei that are larger, so maybe there could be interaction between electron and nuclei. And yes, indeed, there is interaction. It's called internal conversion when electron gets some energy from the nucleus, and electron capture when electron is captured by the nucleus. So these are well-known phenomena observed for large nuclei. Yeah. So and indeed we can see here that indeed this minimal distance is crucial. Yeah. So that it for large nuclei it can be comparable with nuclear size, so there can be interaction between electron and the nucleus. But for small ones, there should be nearly no interaction, and it's not observed. So I think this is very nice to think about it. Okay, so so if we substitute this zero, z equals zero, so that we stay in this plane perpendicular to spin, then the Euler-Lagrange evolution equations become much simpler. Yeah, so it's not so bad, and we can look at them numerically. So here are some solutions for different starting. So we start with like previously in this x equal 1. Yeah, so here we have x equal 1, y equals 0, and z is 0 all the time. And now we start with 0 velocity in x direction, and this chosen varying in y direction. Yeah, so this is the vertical velocity is different. So here is +1, -1, so we get this kind of rotation. Here we have +1, this rotation. Here is even larger, 10, -10, +10. So here we have escape. Here we have Kepler situation, the circular ellipse orbits. Then we have precession 0, 1. So now we can see that this is like for Mercury, but for Mercury it's many orders of magnitude smaller. So we can see this is in one direction, here is the opposite direction. Yeah, so this is very similar, but slightly different. Then we have kind of scattering situation, that is very low angular momentum, and so we fall, and then due to this Lorentz force, the trajectory is bent, and we cannot fall exactly into the central object. And for tiny, even smaller areas, so 0, 0, 1, we get to this 120 degrees as mentioned. Yeah, so to understand this behavior, let's take a look at this dependence from this derivative, like here. What is the change of angle? So here we wait two times this falling time, this quantization time for scattering. So let's wait twice times and calculate the angle, the final angle. If you start with 0, so this is the change of angle now. Yeah, so here is this x prime as previously, and what we can see that for 0 we have this one -120 degrees as we expect. Then something strange is happening here, so we take a look closer here, and then we get close to 0. Yeah, so there is something strange happening here because we go from plus 180 to minus 180. So we can try to unfold this plot. Yeah, so we just glue this one to here and so on. So if you do it, this unfolding, we can see that it looks like this. So it's much more reasonable looking. Yes. So but still we can see that there is some speed up of change here. So to understand what's happening, why is this speed up, we can think about the minimal distance. and turns out that indeed this minimal distance is slightly smaller for if you go below this 0.05, and then rapidly changes the behavior. Yeah, so something strange is happening there. I have some zoom here. So we can see that so because the distance is smaller, so the Lorentz force is getting stronger. So we get this kind of behavior. But the time the minimal distance is has minimum for the free fall, and then it's slightly larger for non-zero initial derivative. Okay, so let's find some interesting solutions. So, for example, we could find the situations where it's 360. So where it crosses 360, 70, 720, so and 1180. So now the after scattering you get the same angle as the initial. So the delta is 0, or multiplicity of 360 degrees. So we get closed trajectories of different angular momentum, different width. Yes, so I think it looks very interesting, especially for regarding the nuclear fusion. Yeah, so if you have electron jumping like this, so in nuclear fusion you have the problem that you have two positively charged nuclei, and you would like to get them together. So the problem is that the Coulomb interaction repels them. So, but if there is electron between them, performing this kind of trajectory, it could screen this Coulomb propulsion. Yeah, so it could make the fusion easier. So I think understanding this mechanism could be very interesting and important to improve fusion approaches to fusion, nuclear fusion. We could also get these bow type time trajectories, kind of similar, but now there is 180 degrees or and further of different angular momentum. It looks like we get the collision with the central object, but we don't have. So instead of collision, the minimal distance is still non-zero. So it is passing close to zero, but it's not exactly touching it. Yeah, so it's very close, but not zero. Then we can get these quantized trajectories. Yes, that we have. We would like to find them 360 degrees divided by k. Let's say for t from k from 3 to 7. So here is for 3, this 0 initial derivative as predicted as wanted. Here is also 3, but for much larger. Yes, one of the maximal. We can see that here is it passes far from this central object. So to this very nice trajectory. Okay, but you have 3, 4, 5, 6. So the period of such trajectories is very close to just this 111 times 2 times the number of scattering. So we get this. So it's not exactly, but very close. Yes, so we can see the one. So these are not exactly, but very close. So we get this quantization of period. So kind of orbit quantization of further multiplicities of some integer, some basic period. So we get the charge quantization here, and so here is taking a look close to this interesting region where the behavior changes. So we can see that indeed there is large dependence from the behavior, from the conditions, from very tiny change of conditions and large change of behavior. So finally, while the previous work was in this perpendicular plane, so now the question is what's happening in the general plane. So, however, this is a difficult question. Yeah. So here we start not from 1, 0, 0, but from 1, 0, 1, still from 0, 0 initial velocity, and we can see that we get this hedgehog. Yeah. So we just go to the center, and then the Lorentz force bends the trajectory, and you get some practically random angle. Is XYZ. So it will be. It's the question is, could we understand this behavior? It's quite difficult. So the simplest question we could try to ask here: what closed trajectory could we get? So especially for this orbit quantization. Yeah. So here you get this flat quantized orbits, but we should also get some flat some quantized orbits which are not flat. So the question is how to find them. And the simplest one seems tetrahedral. Yeah, so that we have this cube, and you'd like to make this scattering like going through these vectors. So the question is, could it find this trajectory? So it's so simple, but it's not. So there is very quick dependence from the parameters. So it needs some search for numerical search, or maybe saying it's not possible. So I'm generally looking for a collaboration for this project. Okay, thank you for the attention.